So let's look at an example.
Sir. Hello?
Yes, Missy.
I was kindly asking if you would explain the first part when you started. I was downloading the app for Zoom because we usually use Google Meet.
Okay, so
I wasn't there for the introduction.
The first part is basically just on the definition of. We're basically emphasizing the fact that atomic structure is split in three respective parts. So these parts includes the electromagnetic radiations. We also have the quantum numbers, and of course, lastly, we have to consider the periodic trends. So this is how we are going to approach atomic structure. So now, in starting it, first we need to consider EMR, which is the atomic electromagnetic radiation, and we have defined this as the propagation of energy through space or medium in form of either magnetic fields or oscillating particles. So now we are saying this electromagnetic radiation has the dual nature property. So when we say dual nature property, we mean it has both the properties of a wave as well as the properties of the particles. So when you talk of the wave, we understand the fact that this energy will be passing through some interference as it is moving from one space to another, which means it will be encountering some interferences, so that those interferences are the ones that are defined by the wave. And of course, we need energy. This same energy will be traveling in or it will be quantized, which means it will be moving in form of packages. So as it is traveling in form of packages, it will be carrying certain energy. So that energy will only be defined by what we are calling as particles. So that's why we are saying it has dual nature, which means it has both properties of the wave as well as that of the particles. Now, of course, we are saying there are basically quite a number of terms that we are going to look at, but to start with, we'll look at the wave, which we have defined as the distance between plates, and then we also have the frequency, which we have defined as the number of wavelength passing through a point in a second. So now the relationship we have said, of course, is that frequency can be defined as the speed of light over the wavelength. And the units we need to work with is that the wavelength, or rather the speed, is measured in meters per second. And of course, we need to ensure that the wavelength is also measured in meters, and this wavelength must be measured in per second in that manner. So now, let's look at an example and see how best this can be explained. So we are saying calculate. So this is from the tutorial sheet. Calculate the frequency of a light containing or having 1.2 centimeter wavelength. So we've been given the wavelength and they are looking for what? The frequency. So now how do we approach such a question? So the first thing first, we need to understand that we know to say frequency is equal to c over the wavelength. So this c is the constant, is the speed of light. So the c is the speed of light, which is equal to 3 times 10 to the power 8 meters per second. Now the wavelength, we are saying this wavelength must be in what? In meters. So what you have been given is in centimeters. which means we have to convert the centimeters to meters. And how do we convert? How many meters make up a centimeter? How many meters make up a centimeter?
I think it's 1 times 10 to the power negative 2 meters.
Okay, that is direct conversion. Huh? So now we are saying 1 meter is usually equal to 100 centimeter. So now, what about in a case where we have 2 centimeter? Of course, this side is same as having an x. So when you do the conversion here, you find that 1.2 centimeter is equivalent to 1.2 times 10 to the power negative 2 meters, because it is like what is cent here, you simply divide it by 100. So now that we have the wavelength and we also have the speed of light, we can substitute in the formula. So we are going to have the speed, which is 3 times 10 to the power 8 meters per second, over the wavelength is 1.2 times 10 to the power negative 2 centimeters. So now what you observe is that the meter and the meter here will cancel. The only thing that will remain is the per second. So can someone punch this on the calculator? What are we going to have? Can you say it again? Two point what?
I think it's 2.5 times 10 to the power 10.
Okay. Is it times 10 to the power 10 per second? So this is our wave, our frequency. So now, what you will notice is that mostly the wavelength that will be given will be in different units, and you'll be required to substitute or to convert. So let's look at some maybe common conversions just to remind you of what you expect. You should understand that 1 meter is equal to 10 to the power 9 nanometers. So be using this conversion to convert. If what you have been given, the wavelength is in nanometers, then this is the conversion. Also, 1 meter is also equal to 10 to the power 10 angstrom. 10 to the power 10 angstrom. So if the conversion is like this, then this is if the units you have been given is in angstrom, then this is the conversion. Also 1 meter is also equal to 10 to the power 12 picometers. Picometers. So if it is in picometer, then you use 10 to the power negative power 12. So maybe these are some of the conversions. And then what about in meter? If it's megameters, what does it mean, megameters or megahertz? Mega means what?
I think it's 10 to the power 6.
So mega is 10 to the power 6. So all those things, please, let's try and see if we can practice them. All right. Now, beside just this relationship we've looked at, which is the frequency, and remember the goal is for us to know, because we are defining wave now, electromagnetic radiation as the energy. So now, how do we find this energy? So we are going to determine this energy by looking at the relationship between now energy and the frequency. So relationship between this frequency and energy. So what it is that energy is equal to H times V, where this H is the Planck's constant. So this is the Planck's constant. So this is also just like speed of light. H is also a constant, which is equal to 6.626 times 10 to the power negative 34 joules second. So these are the units for the Planck's constant. And then V, this V is the frequency. So energy is equal to HV, which means Planck's constant times the frequency of that light. Now, remember we also explained or determined what this frequency is. We know to say frequency is equal to the speed of light over the wavelength, which means if we want to determine energy, remember energy we are saying is equal to HV, but we know what V is. So according to our calculation, we know to say V is C over wavelength. So this further, energy can be defined as energy is further equal to H, where there is V will be placed with that, which means H of HC over the wavelength. So this is the calculation for frequency, energy. So let's look at the tutorial sheet. If you look at the tutorial sheet for chemistry, so question number, so let's look at the tutorial sheet for question number, so question number 2D.